Okay. Okay, so we've got 5 times 10 to the 7th, and make sure my screen is here where I can see what I'm doing. Okay. 5 times 10 to the 7th, and excuse me, second, the camera zoomed itself back a little bit. There's no reason it should do that, but it's got its own idea. Okay. So we got the third time, 5 times 10 to the 7th multiplied by -3 times 10 to the -2nd. Well, we can rearrange this as 5 times -3 times 10 to the 7th times 10 to the -2nd. And we're going to group the 10 to the 7th and the 10 to the -7th. We're going to also multiply the 5 by the -3. Now 10 to the 7th times 10 to the -2nd is 10 to the 7 minus 2. Okay, so we're just using the laws of exponents. And we get -15 times 10 to the 5th. But 15, this isn't scientific notation. 15 is not between 1 and 10. Okay. So we write this as -1.5 times 10. And that times 10 to the 5th. And then 10 times 10 to the 5th. And let's go ahead and write that out. And just to remind ourselves, this 10 is a 10 to the 1. So we see the exponents that we have to add. Here we have -1.5. Badly written 10, but I think you can recognize it. -1.5 times 10 to the 6th. And we never write out a bunch of zeros. Okay. We just use the laws of exponents and we get this. Now, if at the end you want to write that with zeros, well, you know that 10 to the 6th is 1,000,000. So that's going to be $1,500,000. Okay, again, the key is we never write out all the zeros. Maybe at the end we want to write them out and see what it looks like. If there are 387 zeros, maybe we don't write it out. Okay, there might be too many, but we group our powers of 10 here, and we group our numbers that we multiply here. So now we can use the laws of exponents to multiply 10 to the 7th and 10 to the -2nd. It's 10 to the 7 minus 2, which is 10 to the 5th. We multiply our numbers out in front, and we get -15. We notice that -15 isn't between 1 and 10. So we write it as 1.5 times 10. And then we combine these powers of 10 and get our final answer. Okay. So let me have you try one more and see if you can follow identical steps here. Let's try . 3 times 10 to the 5th multiplied by 7 times 10 to the 14th. Okay, unfortunately, I didn't record this as I did it, but here we have 4 times 10 to the 9th over 7 times 10 to the negative 5th. I'm tempted to express 10 to the negative 5th as reciprocal and use the complex fraction idea, but we'll just say that a 10 to the negative 5th in the denominator becomes a 10 to the 5th in the numerator. Okay, so we can rewrite this as so. Now I don't have any powers of 10 in the denominator, and you notice scientific notation doesn't have any powers of 10 in the denominator. So any power of 10 you happen to have in the denominator, you have to have the negative of that power in the numerator. Okay, so 10 to the 9th times 10 to the 5th is 10 to the 9 plus 5. We keep the 4 and the 7 just as they are. And 9 and 5 is 14, so now we got 4 over 7 times 10 to the 14th, which can be written 4/7 times 10 to the 14th. Now this isn't scientific notation. First place scientific notation is going to have a decimal number out in front. Okay, so we'll 4/7, we divide that. 4/7 is approximately 0.57. We can use more significant figures if we wish, depending on the context and exactly what we're trying to accomplish. But for an illustration, 0.57 is perfectly okay. Okay. Now 0.57 is not between 1 and 10. So we have to write the number 5.7 here. And then that's got to be times 10 to the negative 1, because 5.7 times 10 to the negative 1 means 5.7 times 1/10. And if you divide 5.7 by 10, you get 0.57. So we do need to understand this. And you can also understand, well, we move the decimal point 1 to the right, so we have to multiply by 10 to the negative 1. Okay. Now the 10 to the negative 1 and the 10 to the 14th combine to give us 10 to the negative 1 plus 14. So we have 5.7 times 10 to the negative 1.14, which is 5.7 times 10 to the 13th. Okay, well, now this problem has a couple little twists on it, but remember the idea. And let's see how everybody does with it. And there's one little twist near the beginning, and if we don't get that, I'll give a hint. Okay, now, if you're just getting started on this, which might be the case if you're working from the video, keep working until you write out what you think this next step will be, or until you have no clue what the next step would be. Because I'm going to go ahead and show you what the first step is going to be. I want you to figure it out yourself. You'll learn better that way. Okay. So here it is. Spoiler alert. Do it yourself if you haven't done it already until you need to see this. And this is going to be everything we've got here, but the 10 to the 6th in the denominator is going to become a 10 to the negative 6th in the numerator. That goes back to the way complex fractions work. So I'm not going to go through the explanation of that. That's a rule that you can use when you're doing scientific notation. Hopefully you do understand how that relates into reciprocals of reciprocals and so forth. But right there it is. Just as 10 to the negative 5th in the denominator became a 10 to the 5th in the numerator, 10 to the 6th in the denominator will become a 10 to the negative 6th in the numerator. And at this stage, everything is going to unfold very similar to the way it did originally. Okay, so I think we did pretty well with this. Let's just get it down here so everybody has it for reference. This is 8 times 10 to the negative 5 minus 6 over 3, which is 8 times 10 to the negative 11 over 3. And that's just 8/3 times 10 to the negative 11th. 8/3 is between 1 and 10, but we're going to write it out as a decimal. It's 2.67. approximately. It's actually 2.6666 repeating. 2.6 repeating. We're going to just round it off to an appropriate level of precision. And there we have it. That's 0. Okay. Yeah, this is it. We don't do anything with this. Now we could then write this out in decimal form. Okay. So the result in scientific notation. Same result in decimal form. We write our 2.6, and our decimal is here. I'm not going to write the decimal. I'm going to count from here. I count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places and put a decimal here. So my decimal is moved from here to here. And then we often want to put a 0 in front of it. So that's more or less optional, depending on who you're writing it for. Okay. So this is the same as this. But if we're staying in scientific notation, this is it. Okay, there are certain products that come up a lot when we're expanding polynomials. And since we're now into polynomials, one of those products is just the square of a plus b. So, can you write out what the square of a plus b would be? And remember what a square is. Okay, so write out what you think the square of a plus b would be. The very first step in finding the expression that's the square of a plus b. But when you square something, you multiply it by itself. 3 squared means what? 3 times 3. Okay, 10 squared means what? 10 times 10. 10 cubed means what? 10 times 10 times 10. Okay, so when you square a plus b, that means you're finding what you get when you multiply a plus b times a plus b. Okay, so let's have everybody just see if you can calculate the product of a plus b times a plus b. Okay, the most common answer I get when we do this is, well, that ought to be a squared plus b squared. A squared plus b squared. It's like the squaring distributes over addition. But squaring doesn't distribute over addition. Multiplication distributes over addition. Squaring doesn't. If you write out a plus b times a plus b, well, you might still be tempted. I mean, it kind of looks right to just multiply a times a and then multiply b times b. But why would you multiply a times a and b times b, but not a times b or b times a? If you're going to multiply things over here by things over here, you better multiply them all. Well, that can get a little confusing, but we have the distributive law. Okay. So this equals a plus b multiplied by something is a times that something plus b times that something. Okay, your law is using something besides a's and b's. I'll say And that's not the order I want to write that in. All right, again. X plus y multiplied by z means you multiply x by z and you multiply y by z. Okay, so we're treating this a plus b as like x plus y, and we're treating this a plus b just as your z. So if I multiply x plus y by something, I get x times that something plus y times that something. If I multiply a plus b times this something, I get a times that something plus b times that something. And then, of course, now I got a times a plus b. Well, that's just a times a plus a times b. And the rule for that is if you multiply x by y plus z, you got to multiply x by y. And then you got to multiply x by z. Okay, then, of course, we apply that rule here and we apply it here. B times a plus b is b times a plus b times b. Well, that could be simplified. You have a times a plus a times b. B times a is the same as a times b because multiplication doesn't depend on the order. That'd be another a times b and b times b. Now, of course, a times a is a squared. A times b, well, a times b plus a times b is 2 a times b, and b times b is b squared. So a plus b quantity squared is a squared plus 2ab plus b squared. Let's find the square of 2x plus 3y. And we could write out the distributive law and do it. It would look a whole lot like this, except we'd have some numbers to go along with it. This is just a plus b squared with a equal to 2x and b equal to 3y. Now, do we see this? If a just stands for 2x and b stands for 3y, then a plus b squared stands for 2x plus 3y squared. Does that make sense? Okay. Well, if a plus b quantity squared is a squared plus 2ab plus b squared, we replace a by 2x we'll replace all the a's by 2x. So a squared is going to be the square of 2x. 2ab will be 2 times 2x. And then it's times b. But of course, b is 3y. So now we can replace b with 3y. And we get this. And then we can do the arithmetic. Square 2x. By the rules of exponents, that means we do 2 squared times x squared. And then 2 times 2x times 3y. Multiply the numbers. 2 times 2 is 4. Multiply that by 3, we get 12. And we get an x and a y. And then if we square 3y, that's 3 squared times y squared. And now 2 squared is 4, so we write 2 squared x squared is 4 squared. Then we have 12xy. And then 3 squared is 9, so 3 squared y squared is 9y squared. And there we have it. Well, that's an example. So let me ask you to see if you can follow what I did. And calculate the square of 4p plus 2q. Using just this formula, a squared plus 2ab plus b squared. Figure out what a is. So let me give you just a little hint. This is part of the a plus b squared if you let a equal what and b equal what. Okay, see if we can answer that question. Okay, we did quite well with this. Most everybody here just skipped this step, identifying A and B, because they saw right away what it was. That's great, but just in case, A is going to be 4p, and B is going to be 2q. So A plus B quantity squared. Let me do it over here. The camera will have a better angle over here. Okay. This is A squared plus 2ab plus b squared. Square of 4b plus 2q is, just say b is p, 4p squared plus 2ab will be 2 times 4p times 2q plus b squared, which is the square of 2q. That equals 4 squared times p squared. 2 times 4 is 8, and times 2 is 16. That's p times q. And square of 2q is 2 squared q squared. So that's 16p squared plus 16pq plus 4q squared. And there it is. Okay, that was quite well done. Hopefully everybody did well with that, and if not, few steps here and the steps in the previous example. And open math is going to give you much more information, additional examples, and additional explanation if you need it. A lot of people apparently, at least here, are going to need that. So I think we're in pretty good shape. Very good. Now, there are other special products that we'll mention. Of course, well, let's do this one. This is kind of important. What's A plus B times A minus B? Okay, let's see if we can work this one out with the distributive law. And if you want the example that we used in working out A plus B squared, hopefully that's how good we'll get. That'll work. You need a reference. You just keep your wits about you and apply the distributive law, and everything should work out. Okay, now we want to review the rules for distributive law. And if you're not real familiar with the rules for the distributive law, you probably want to write it out and refer to it at least the first few times you use it. You do need to wean yourself from having to have it written out in front of you, because of course, when you take a test or something or need to use it later on, it becomes something that really needs to be second nature. And it does if you use it often enough. Okay, so the rule is, again, if you got X plus Y multiplied by something, it's X times that something plus Y times that something. If you got X multiplied by a sum of two things, it's X times that first thing plus X times the second thing. Now we're going to apply that to this special product. So this equals A times A minus B plus B times A minus C. And then we apply it again. A times A minus B is A times A minus A times B. And then B times A minus B is B times A minus B times B. So I'm just going to put parentheses around these just to indicate that these two come from here, these two come from here. But I really don't need the parentheses, and I'm not going to write them in the next step. Okay, well, A times A is A squared. Then we got minus A times B. But then we got plus B times A, which is the same as A times B. And then we have minus B squared. Okay. Well, what's minus A times B plus A times B? That's zero. That's minus of something plus of something. Okay. That just leaves us A squared minus B squared. So A plus B times A minus B is A squared minus B squared. Now, since people saw this pretty easily, I'm not going to ask you to square a difference of two binomials. Well, yeah, this doesn't. I'm not going to ask you to do a sum and difference of two binomials or two expressions. And I still haven't said it right, but I hope you know what I mean. Doesn't matter. Okay, A plus B times A minus B is A squared minus B squared. The question is, can you write 4x squared minus 9y squared in the form a plus b times a minus b. And give you a start on this. All right, a squared minus b squared here, 4x squared minus 9y squared here. Okay. If this is in the form of this, what does a equal? And what does b equal? Okay. Well, what would you square to get 4x? 4x squared has to be an a squared, okay? Well, give you the answer. If you square 2x, you get 4x. So 4x squared is going to be a squared. A has to be 2x. So whatever you get here, if you square it, you got to get this, okay? And b, well, if b squared is 9y squared, then b has to be 3y. Okay, so now if I want to do a squared minus b squared, well, a squared minus b squared equals a plus b times a minus b. Once I identify that this has the form of a squared minus b squared, and once I identify what a and b have to be, I can just write out formula. And it comes out a is 2x, so I have 2x plus 3y. And a minus b will be 2x minus 3y. Okay, so that's kind of a big deal. You'll see that in the homework. So, we're out of time, so we could do more special products. You're going to see them in the open math. They work. You can understand them in a similar way to the way you understand these.